Hello, my name is Alessandro, and today I'm going to talk about Experiment 4 from the Aerospace Laboratory course at UC Irvine, which deals with pressure distributions over airfoils to measure pressure coefficients as well as lift and drag coefficients at various angles of attack. I will first discuss the objectives of the experiment before briefly summarizing the fundamental concepts, such as pressure distributions, wake deficit drag measurements, and hot wire anemometry. Next, I will describe the procedure used during the experiment, and finally, I will explain the most important results and conclusions of the experiment. The objectives of this experiment are, first, to measure the pressure distribution over a Clark Y14 airfoil at various angles of attack, in other words, to find the pressure as a function of alpha. Secondly, the objective is to determine the lift and drag forces from the pressure measurements, and then to compute the corresponding lift and drag coefficients. Also, the goal is to estimate the drag coefficient from the downstream velocity distribution using the wake deficit method. The final objective is to compare the lift and drag coefficients computed from the pressure distribution and velocity distribution to those obtained using the sting balance from experiment 3 during the previous lab. So, as an object, such as an airfoil, passes through a flow field, changes in fluid momentum impart a series of forces along the entire perimeter of the airfoil. This force, which is called pressure force, acts normal to the surface of the airfoil at each point and creates a pressure distribution. Pressure is scalar and does not have a direction. The sum of the pressure distributions along the entire airfoil give two resultant forces, one in the vertical direction, which we call lift, and one in the horizontal direction, which we call drag. Intuitively, we can see that low pressure over the top of an airfoil, where air speeds up, and high pressure beneath it act to push the airfoil up. This force is the result of the pressure gradient and can also generate drag at high angles of attack. In the equations below, the analytical solution involves contributions of both the pressure gradient and the sum of shear stresses along the airfoil. But here we neglect the shear stresses and see that we can find lift and drag from pressure alone. Another way to measure the drag on an object such as an airfoil is to measure the velocity profile of its wake. Assuming that the static pressure is constant along the control volume and that the momentum is conserved, we expect that the effect of drag is evident in the momentum deficit in the wake of an object. Applying numerical integration to the momentum equation from fluid dynamics combined with a mass conservation equation gives us the following results for the drag force. Here we see that the equation for drag involves subtracting the velocity profile upstream to the one downstream of the object, and multiplying this deficit with the downstream velocity gives us the drag force. By calculating the drag, we can easily find the drag coefficient as well. Hot wire anemometry is used to find flow velocity quickly and precisely. Although anemometers can be fragile and intrusive in wind tunnels, they sample continuously, have small spatial averaging, and they have a fast frequency response. Also, the strong signal to noise ratio produces good velocity measurements and tracks small changes effectively. How does it work? First, the wire is heated. As fluid flows over the wire, forced convection cools the wire, which changes its resistance. If you look at the Wheatstone bridge circuit used by the anemometer, you will see that the circuit inputs a voltage to counter the change in resistance, keeping the temperature steady. This sort of anemometer is called a constant temperature anemometer, or CTA. The voltage produced by the circuit is proportional to the flow velocity, and thus enables us to measure the airspeed precisely. To begin the experiment, the first step is to calibrate the hot wire anemometer using the adjusted King's law, where n is taken to be 0.45 instead of 0.5. We also see in the equation that E is the voltage and U is the velocity. Next, the wing model with the static pressure taps is installed vertically in the wind tunnel. The static pressure of the test section is connected to the low pressure side of the pressure transducer for reference, and the numbered pressure taps are individually connected to the high pressure side of the transducer. To measure the pressure force, LabVIEW is used to output the difference between the static pressure upstream and the static pressure measured on the surface of the airfoil at the static pressure tap locations. This pressure difference is used in the equation to find the pressure coefficient, as shown. Q is the dynamic pressure and is constant through the experiment. For this experiment, the velocity was 25 meters per second, and the angles of attack were 0, 4, 8, and 20 degrees for the airfoil. Next, the hot wire anemometer is placed behind the airfoil to measure the wake velocity profile using the same 25 meter per second upstream velocity and angle of attacks from before. Shown here are tabulated values of the lift and drag coefficients determined from both experiment 4 and the previous experiment, as well as the NACA report values. We immediately notice that experiment 4's lift coefficients match the NACA values more precisely than those of experiment 3, but we also notice the drag coefficients using experiment 4's wake deficit method are slightly less accurate than those obtained from experiment 3. To the right, we see graphical representations of both the lift and drag coefficients as a function of the angle of attack. Here are graphs of the pressure coefficients at 4 different angles of attack. For low angles of attack, we see that the pressure coefficients vary with chord length but stay consistently low. For large angles of attack, we begin to see higher coefficients of pressure on the upper surfaces, and the peaks of pressure come earlier. This is consistent with the expectation that center of pressure moves forward on the airfoil as the angle of attack increases, and that there would be a visible effect on the coefficients of pressure. A coefficient of pressure of 1 implies that all the dynamic pressure has converted to static pressure, and for a cambered airfoil like the Clark Y14, we expect that the upper surface should have low pressure at the top initially, and a lot of adverse pressure at high angles of attack, and this is what we see here. It was also possible to graphically determine the pressure distributions on both the upper and lower surfaces of the Clark Y14 airfoil for 4 different angles of attack, and the results are shown here. We see great results at every angle of attack. At alpha equals 0, there's very little difference in pressure between the two surfaces, but as the angle of attack increases, we begin to see a massive drop in the pressure on the upper surface that corresponds to increased lift generation as the normal pressure on the lower surface increases. At a high angle of attack, this pressure gradient begins to increase drag, and at 20 degrees, we can infer the effects of boundary layer separation at about 60% of the chord length when the pressures begin to match. Some major findings are that the pressure drag is only sizable at high angles of attack, such as 20 degrees. Also, the wake deficit rose markedly at high angles of attack, which confirm the predictions of flow separation and stall at an angle of attack of 20 degrees, which is beyond the roughly 15-degree stall limit. The coefficient of pressure, as well as the lift and drag coefficients, all increased as the angle of attack increased, as expected using the wake deficit method. Also, it is interesting that the lift coefficients are more accurate in experiment 4. This is likely because the pressure distributions measured by the static taps and pressure transducers are relatively error-free and yield reliable results. However, the drag coefficients measured in experiment 3 match more closely to the NACA results compared to the drag coefficients measured in experiment 4. This is likely because the wake deficit method used in experiment 4 is more sensitive to instrument error, since the velocity distribution must be carefully measured with the anemometer. However, experiment 4's comparative success with measuring the lift coefficient means that it remains a valuable lab procedure and that careful drag measurements can be standardized in the future. This concludes the presentation. Thank you for watching.